All right, so this is our introduction to combustion. First of all, we have to describe the reaction having to begin with some reactants and end with some products. Now, sometimes in chemistry they'll have an arrow indicating that after the combustion process or after the chemical reaction, there can be some reactants remaining in equilibrium with some of the products. And then sometimes there's just a single arrow. So you go from reactants to products. What does the single arrow signify versus the double arrow? No reactants left. So we assume it's complete. So the assumption is it's complete. The reaction goes all the way. It's all the way to the right or all the way forward, okay? So there's no reactants left after the process known as combustion. The type of combustion we're going to study is typically a hydrocarbon fuel. You should know some of the fuels. One fuel would be methane. What is the makeup of methane? It's CH4. So there is the carbon with 4 hydrogens. So it's a hydrocarbon fuel. What's another hydrocarbon fuel that we might use? Propane. What's propane? C3H8. What's another one? Octane. CH818. And these are the simple ones. You know, the propane, the methane, the octane. Those are very simple. Now, this may ring a bell with gasoline, right? Like the octane number, octane rating. But gasoline is not one pure element. It's not pure octane. If it was, the benchmark would be it would have an octane rating of 100. And our fuels, like gasoline that you buy, is a mixture of a lot of things in it, a lot of different hydrocarbons. But this is kind of a benchmark for gasoline. If you're going to pick one, you pick something like, I'm going to model something like C8H18, pure octane modeling gasoline. Sometimes there's some oxygen in the fuel. Ethyl, alcohol, having the C2H5OH. And so it's primarily a hydrocarbon fuel, but what does it have a little bit of? A little oxygen in it. Not only ethyl alcohol, but methyl alcohol, CH3OH. How many people buy gasoline and then you look and you say, we've added up to 10%. What did they add up to 10% of in your fuel? Ethanol. So why they added this, right? Why do they force sellers of gasoline to have that 10% in certain select cities and zones or regions? Subsidized corn, okay, yeah. That may be the truth, but what's the rationale for it? That oxygen helped it burn a little cleaner. And so in the EPA non-attainment zones, where they have problems with air pollution, they mandate one of the remedies to help reduce the air pollution is have some oxygenated fuel. So have up to 10% ethanol mixed with the gasoline. It's more complicated than that, but the simple truth is there's oxygen in that fuel to help promote the complete combustion. Sometimes you'll have all hydrogen. What is that? It's just hydrogen. H2. You mean I can go down to a filling station and buy hydrogen? No, but you can go to a gas supplier and buy hydrogen, true. Or if you're NASA and you really want to have a rocket with a lot of kick and you want to push off, you get hydrogen. And so you can study the combustion of hydrogen, but there's no carbon with it. And sometimes you have fuels that are all carbon. Or I know that the pure tank of hydrogen it's a good gas. You paid a lot of money for the bottle of hydrogen, and it's pure hydrogen. Now carbon, we don't really have pure carbon, but something that's close to all carbon is coal. And you have different types of coal from different regions of the country, and you can have higher and higher concentration or percentages, mass fractions or weight fractions, the different ways they describe what's the makeup of the coal. It has some sulfur in it, has some hydrogen in it, but coal is primarily carbon. All right, and then more expensive coal has higher grade, higher levels of carbon. The cheaper coal will be lower amounts of carbon in it. So that's all of our fuels. What is our oxidizer? Our oxidizer is oxygen. Oxygen. And so where do we get our oxygen from? Well, you can go down and you can buy a bottle of pure oxygen from the gas supplier. And maybe you want to have a cutting torch. You'll have an oxygen bottle, a acetylene bottle, and you'll mix them, and you'll have a little, so that really has a high temperature for the combustion. But that's very expensive. We like to combust things in our automobile engines. Where do we get the oxygen from? We get it from the air. So we ingest the air. Why do we ingest the air? Not for the nitrogen. We'd love to just have pure oxygen ingested into our internal combustion engines. But that's not going to happen. So you get the oxygen from the air. So what is air? Air is a complicated mixture, but we simplify it to two components. So the air that we would breathe in this room, I know there's CO2 in, argon, and some other odors. Maybe your nose is sensitive, can tell what the odors are in this room, some volatile organic compounds. But we would model it as 79% nitrogen and 21% oxygen. And that makes 100% air. So if I have 1 kilomole of air, how many kilomoles do I have of nitrogen? And how many kilomoles do I have of oxygen? If I have 1 kilomole of air, it's not a hard question, but 0.79 and 0.21. Make sense? Now, if I take this equation and I multiply by 1 over 0.21, is it still a valid equation? And you pull out your calculator and you say, first of all, I won't need it for the coefficient in front of how many kilomoles of oxygen there are. I think I can do that math in my head. 0.21 divided by 0.21 is 1. So I'll have 1 kilomole of oxygen, but how many kilomoles of nitrogen will I have? 3.76 with some change, but the book rounds off the rest of those digits, and it's just 3.76 kilomoles of nitrogen. And then if I take 1 divided by 0.21, I'll get 4.76 kilomoles of air. And so when we talk about oxygen coming from air, we often use an equation like this. We'll say we're interested in getting 1 kilomole of oxygen in. In order to get 1 kilomole of oxygen from air, I have to bring in, mixed with it, 3.76 kilomoles of nitrogen, which means to get 1 kilomole of oxygen in, I have to bring in 4.76 kilomoles of air. Where do the products go? We started primarily with the hydrocarbon fuel. Well, when you bust it up and rearrange it in a chemical combustion like the methane, CH4, and you're going to combust it with pure oxygen, and there is an application where they do have methane and they do combust it with pure oxygen. That would be a cheap way to cut up metal. And I think they use that over in Seguin when they dice up a lot of scrap metal. They're not really burning acetylene, they're burning methane with an oxygen, and they produce oxygen on site because they use so much of it. All right, and the methane's cheap. So you can have a cutting torch of methane and oxygen. Where does it go? The carbon goes to CO2. How do you know that? How do we know this? It's just like this. How does oxygen float around in the air that you're breathing? Does it float around as O, O2, O3, O5, whatever? That's why you study chemistry. It likes to float around as O2. Professor, you're a mechanical engineering professor, prove it to me. There's other people out there called chemistry professors. And they look at the orbital configuration of electrons, right? And they say things are happiest when the O is with the O, and it floats around as O2. It doesn't like to float around as O. It doesn't like to float around as O3. So that's my mechanical engineering explanation for why oxygen likes to float around as diatomic oxygen. Same thing when they look at how carbon and oxygen get together to make carbon dioxide. It doesn't like to float around as carbon monoxide. Actually, that likes to react with other things, and when you ingest it into your lung, it likes to react and block off getting oxygen into your bloodstream, and then you die of asphyxiation, lack of oxygen. So it likes to react with other things, and so if you have other things with CO, it won't be long, and it won't be CO anymore. It'll be, but CO2 is kind of content. Don't ask me why C2O5 doesn't like to float. I don't know. That's the chemistry people can tell you. But CO2 is the way it likes to float around. So the carbon likes to go to CO2 and the hydrogen likes to go to H2O. You know, why doesn't it like to go to H2O2, right? You heard that chemistry joke? It's like grade school level. Somebody goes in the restaurant and says, I like a drink. What would you like to drink? He says, I'd like H2O. Oh, you want water, right? And they ask the next person, the companion at the table, what would you like too? I like H2O too. And then they drink it and they die because it's, right? You remember that joke? H2O2 is, I forgot the name of it now. Poison, yeah. What is it? Hydrogen peroxide, I think that's what it is. So don't drink hydrogen peroxide. It's not good for you, right? So anyway, it doesn't float around like that. It likes to float around as H2O. So basically, you start off and you're going to write some reaction equations. You have to know what the fuel is, what's the oxygen source or the oxygenator, and then what's the products, and the happy products are CO2 and water vapor. So what we want to do is we want to write a chemical reaction equation. Everything is on a kilomole basis or amount basis or molar basis, right? And I know that I started writing air as 1 kilomole, of air, or 4.76 kilomoles of air. But what we do is we just leave off the kilomole, it's implied, and we put our coefficients in front. So let's go back. Let's start and say I have methane, CH4, and I'm going to get the oxygen from the air. This is the way we write it for air, meaning that I'd like to do this. I'd like to have a 1 in front of that O2. It makes the math a little easier. And so what I'm going to do is for every 1 of the O2, I know that I have to bring along, so put it in a parenthesis, 3.76 kilomoles of N2. It's going to go to complete combustion. All the carbon's going to end up in a carbon dioxide. And all the hydrogen will end up in H2O. And I didn't leave enough room over here. Let me try and just move it over so it looks pretty. And then what you're going to do is you're going to, for just a perfect amount of air, the 100% theoretical air, not any excess or any deficient air, just a perfect amount of oxygen, you're not going to have any O2 in the products. There's 0. But you're going to have N2 going out. And because we like to play with this 3.76, just go ahead and put it right there. It helps balance the equation. Start the reaction equation with this much methane. There is really a 1 in front of that CH4. Sometimes I never write it. It's implied. It's just CH4. Whatever you do, here's rule number 1. Don't play with the 1 in front of the CH4. when you're a freshman or something, you're tempted to start monkeying around with this coefficient, that coefficient. Do everything on 1 mole or kilomole of the fuel. And what we don't know, how much air we have to bring in to get the right amount of oxygen. We don't know how much CO2 is produced, and we don't know how much water vapor, H2O, is produced, and we're going to have to finish out the balance on the nitrogen. So a lot of times they'll start and say, oh, well, we have an unknown coefficient A, an unknown coefficient B, an unknown coefficient C, and an unknown coefficient D, and then we solve for those coefficients. Does this sound familiar? You have different balances. The carbon has to balance. The hydrogen has to balance. The oxygen has to balance. And the nitrogen has to balance. At this point, you're tempted to say, yeah, I can see the C. It's one of them sitting right there. That's great. I could see the hydrogen. There's 4 of them sitting right there. And the oxygen, but sometimes you're tempted to try to balance O2 instead of O. Don't do it. Just balance O. Don't balance the O2. Just like you'd be tempted to balance the N2. Don't do it. Just balance N by itself. All right. So for the carbon balance, you're leaving a 1 in front of the fuel. Don't go playing with that. Don't change it. You're going to have on the left-hand side 1. I don't see how many kilomoles of carbon are there? Just 1. If I have 1 mole of methane or kilomole of methane, and I don't care how many kilomoles of air I bring in, there's no carbon with it. So that has to equal the number of kilomoles of carbon on the other side. I look, for every CO2, there's 1 of them. So I have A times 1. And then I have B times 0 and D times 0. You just leave that all off. The carbon's only in the carbon dioxide. Right away I can solve for the unknown coefficient A. True? What's the unknown coefficient A? It's just 1 for this problem. Boom, you're done. Do the hydrogen balance. How many do I have? I have 4 with every kilomole of fuel, and I'm only bringing 1 kilomole of fuel. And I have none with the air, so I'm not going to put plus 0 times C. There's nothing with air. And then I look over here, for every B kilomoles of H2O, how many hydrogens do I have? 2. So we can solve for B. And B is 2. Now let's solve for the oxygen. Gets a little trickier here. So we have C times O2. So we have 2C. Did I do that right for the left-hand side? 2C. And then I come over here. I have 1. I already solved for A. I know it's 1. I'm going to write it as A times 2 for the how many oxygens are in the CO2. And then I'm going to have B times 1 for how many oxygens in the water. And then I'm going to have, I could put D, E, how about E times O2? E times 2 if I had some oxygen. But for complete combustion, I have the assumption that there's no E, right? All right. Well, guess what this equation allows us to do? If I just put in the number for A, that was 1, wasn't it? And B, which is 2, then that's 2 plus 2. Is that 4? On the right-hand side, in the products, I have 4 oxygens. Hence, how large does C have to be? C has to be 2. Make sense? So it's like I balanced the carbon forward, I balanced the hydrogen forward, I balanced the oxygen backward to get the coefficient that's on the left-hand side in front of the air. And then if you got those 3, it's easy. For the nitrogen, you just say, okay, what do I need D to be? 2. Now, that's why you left the 3.76 right here. It's 3.76 right there, so it's just 2. Makes it easy on the math. Yes, sir.
You got the 2C from the 2O2 and the 2N2, right?
Right. Are you talking about the oxygen or the carbon? Because you said the CO2, I have 2 O's. And here I have 2 O's. And so that's 4 O's. Right. And then I look back over on the other side. So that's theoretical air. As soon as you get down theoretical air, 100%, the perfect amount of air, having no oxygen left over, then they play with it, and guess what they do? They say, we have excess air. And often in combustion processes, you do have excess air, 10%, 20% excess air, okay? Or even higher. So what do you do for excess air? The recipe is get the theoretical air balanced stoichiometric equation with all these coefficients. These stoichiometric coefficients are the coefficients in front. The 1 is the stoichiometric coefficient on the methane. This 1 is the coefficient on the CO2, etc. Once you get it balanced for the theoretical air, then if you have excess air, how do you modify that equation? Come back and play with doing something right here in front of this amount for the perfect amount of air. So if I said I had 20% excess, that would mean I have 100% of the theoretical air plus 20% excess, true? Isn't that 1.2? Isn't that 1.2? And then I would just stick the 1.2 in front of the 100% theoretical air. Now, maybe I need to clean this up a little bit. Should I clean it up and rewrite it so it's a little easier to see? Let's write it all out. I'll start. So we start with the CH4. We're going to leave some extra room. We had 2 times O2 plus 3.76 N2, and that is my 100% theoretical air. It combusts to give 1 CO2, 2 H2Os. Now we will leave a little room for O2, and we still have 2 times 3.76 N2. So what we do is we modify right here. We say, okay, we have 120% theoretical air. 100% of it is already taken care of. It's 20% that I need to now consider and rebalance the rest of the equation. So the carbons, does this coefficient in front of the carbon dioxide change? No, because all I did was bring in more air, and air had no carbon with it. And I left the 1 here. I didn't change the amount of fuel. Does the 2 in front of the water, H2O, change? Same reason. What was the reason? There was no hydrogen in the air. And so if I brought in a little extra air, it didn't bring in any extra hydrogen. The hydrogen's controlled by the hydrogen in the fuel. But right here, I have to rebalance my oxygen and my nitrogen. Which one do you think is easier, the oxygen to rebalance or the nitrogen to rebalance? Nitrogen is a little easier. What's the coefficient that goes right in front of this one for the nitrogen? 1.2. All right. Now the hard one, the oxygen. I pause and I let you write it down on your paper. Okay, so yeah, I get that question about every semester. So they'll say, hey, I was taught in chemistry that I need to always have integer numbers. But as soon as you have air and nitrogen, oxygen coming from air, it's not a nice number. It's 0.21, 0.79. So I think what happens theoretically, or when you first were exposed to chemistry, is your math skills weren't that strong. And you could add whole numbers, but you didn't work so well in fractions, maybe in high school. And so then that's just a legacy carryover. Like, okay, it's easy to add and subtract numbers if they're whole numbers. But hey, we're senior level mechanical engineering students. I think we can work with fractions now with confidence. That's all I can say. There's no rule that says you have to work in whole numbers, right? All right, so the answer is that it's 0.4, true? And so how did you do that? Math. That's good. One thing is 100%. Remember, this 1.2 is 100% plus 20%, right? So it was really only the 0.2 of this part that needs to be accounted for. So the 0.2 times the 2 gives me 0.4, and that's what was left over. All right? So it's like if, let's say they said this number was, I don't know, phi, and phi is something greater than 1. Maybe phi is 1.3 this time, right? This number right here is going to be 1, a phi minus 1, get rid of the 100% off of it, just what is above 100%. 0.2, 0.3, whatever the number is above the 100%, and then make sure multiply by that coefficient. And there it is. True? Now, there's many ways to get that. You can go back and rebalance all of the oxygen, but really what you needed to rebalance was only the excess oxygen, which was 1 minus, or phi minus 1, if phi is greater than 1. Okay. What about when you have deficient air? This is a real challenge because you don't know. Did let's say it was 80% or 20% deficient air or 80% theoretical air. So you come in here and you go 0.8 times the 2 times the O2 plus 3.76 N2, right? Now, what happens CH4? Oh, don't play with that coefficient. You'll be tempted again and again to start playing with the coefficient in front of the CH4. Leave it 1. Got it? Okay. So if I don't have that many oxygen, can I really get 1 CO2 and can I get really 2 H2Os? No, these have to be reevaluated. You could say, well, why don't we just do this? Why don't we just say that instead of 100% of our methane being combusted, because we only have 80% oxygen, that we'll do this. We'll just say that 0.8 here and 2 times 0.8, and that's a pretty good approach to it. And then what you're going to have is 0.2 times CH4 coming out. You're going to have some unburned methane coming out because you didn't have enough oxygen, true? But in reality, when you don't give it enough oxygen, you may not get that much fuel out. You may start to get something called CO out, carbon monoxide. And so unless you're told the makeup of the products, you're just going to be guessing what the products are. Well, I think all the unburned methane will just go out as methane. Probably not. Okay? So it looks like excess and deficient air are just as easy to analyze. Not really. Okay? Deficient air is a real challenge at times because you don't know what happens to the fuel. Does it partially combust and go to CO? Like it's ready to continue to get to CO2? Or does it just kind of go through? Some of it completely combusts and some of it doesn't combust at all. All right. Now we have some metrics that we can talk about the performance of the system. One is the air-fuel ratio. It can be done on a mass basis or on a molar basis. So they use a symbol, air to fuel, AF. Yes, sir. It's defined as the mass of air divided by the mass of fuel for that reaction equation. And then on a molar basis, A to F. And what do you think they do to this to make it different symbol when it's a molar basis? They put a bar over it. So they say, oh, this is a molar air-to-fuel ratio. And the molar air-to-fuel ratio is defined as the number of moles of air to the number of moles of fuel. All right, and then guess what the fuel-to-air ratio is? Guess what symbol they use? F to A instead of A to F. And if it's on a mass basis, it's the mass of fuel to the mass of air. Is that equal to the air-to-fuel ratio reciprocal of? Sure, sure. And then they can put the fuel-to-air ratio on a molar basis. Number of moles of fuel to number of moles of air, that's just air to fuel on a molar basis, reciprocal. Yeah. Okay. So once you get one of them down, it's pretty straightforward. How would I jump between the mass basis and the molar basis? Well, is this equal to the number of moles of air times the molar mass of air? Would that give me the mass of air? And is this equal to the number of moles of fuel times the molar mass of the fuel? And then we look at this, what is that equal to? So what we find is the air to fuel on a mass basis is the air to fuel on a molar basis times the molar mass of air divided by the molar mass of fuel. Consider the complete combustion of benzene C6H6 with 100% theoretical air. Obtain a balanced reaction equation. So I start C6H6. I'm going to have it with theoretical air. So it's O2 plus 3.76 N2. And I have an unknown coefficient that I need to find, the balanced equation. Complete combustion, single arrow over 2. I know that there's going to be carbon dioxide. I know there's going to be water vapor. And I know that there's going to be nitrogen without any unused oxygen. So the first one I balance is carbon moving forward. So if I balance the carbon going forward, what do I pick up right here? Is that a 6? Is it 3 for the hydrogen balance? Now go backwards for the oxygen to get the coefficient in front of the air. I always do this slowly because this is very error prone. How many do I have from right here? 12. How many do I have from right here? 3. I can add that with confidence. 15. What I like to do is I like to do it this way. 15 divided by 2. It's a little less error prone. Because when I multiply by 2, I'll have 15 over 2, and I have O2s, then I'll have the right amount of O's. Make sense? Somebody says, well, I'm just going to put 7.5 there. Works for me. Put 7.5 or 15 over 2. And then we have to finish it out. We have the 15 over 2 times 3.76 N2s. Part B. All right, air to fuel on a molar basis. Is that the right symbol? So how many moles of air do I have? 7.5, 15 over 2, times, this is where a student will make a mistake. It's 1 plus 3.76, or it's 4.76. I'll have this on the final exam. I'm going to tell you, I'm going to have a problem like this on the final exam. And right here is where a student, maybe 10% of the class, 15% of the class will just wipe out. Because I'll ask them to compute the air-to-fuel ratio, and there'll be air in there. But to get 1 mole of oxygen, I need to carry along 3.76 moles of nitrogen, meaning I have to ingest 4.76 moles of air. Make sense? So that's how many moles I bring in of the air. For how many moles of fuel? I left that 1 in front of the coefficient, in front of that benzene. And so that's your air-to-fuel ratio on a molar basis. What about the air-to-fuel ratio on a mass basis? Well, it'll be the 7.5 times the 4.76 times the 28.97. That's the molar mass of the air. So then I have to go and look up the molar mass of the benzene. The molar mass of the benzene is 78.11. And so the air-to-fuel is 13.2. On a molar basis, the air-to-fuel was 35.7. What's the mole fraction of water in the products? Y of H2O in the products. Well, I'm going to have 3 kilomoles of water vapor in the products. And in the products, I have 6 of the carbon dioxide, 3 of the water, and 15 over 2 times 3.76 of the nitrogen. So the mole fraction of water vapor in the products comes in at 8.06%. And then for part E, what is the dew point temperature? Well, I have to assume the total pressure is atmospheric pressure, 101.3 kilopascal. Hence, the vapor pressure is going to be the mole fraction of the vapor in the products times the total pressure. The vapor pressure comes in at a whopping 8.17 kilopascal. Then I look up the saturation temperature at that vapor pressure to get the dew point temperature, and the dew point temperature comes in right around 41.9, 42 degrees C. Any questions? Thank you for your attention.